All right, guys, we're going to continue with chapter 2 and section 2.2. This is going to be a long video, so just bear with me. There's a lot of important stuff in this section. So let's get going. A density curve is a curve that is always on or above the horizontal axis. In addition, the area under a density curve is always equal to 1. The density curve describes the overall pattern of the distribution. And the area underneath and above any interval of the values on the horizontal axis is the proportion of all observations that fall in that interval. So what we're doing here is we're actually creating a curve to estimate what the percentage of the proportion that fall in between that interval. Because it's easier to find the area under a curve than it is to use kind of those values that are in our histogram or something like that to find that area. So there's actually a little bit of a reference in this stuff to calculus. So it says fit a smooth curve to estimate the distribution of the histogram below. All you're doing when you're fitting a curve is you're just kind of drawing in an estimate of what the curve would be that represents that histogram. We kind of have done that in the past with some of the histograms when we're using it to describe the shape. When you're describing a density curve, you want to think of the median as the equal areas point of that histogram or that curve, okay? So the point that divides the area under the curve in half. So while the median is the equal area point, the mean you want to think of as the balance point, at which point the curve would balance if it was made of solid material. We talked about this in the last chapter, that the median and the mean are the same for a symmetric distribution or a symmetric density curve. They both lie at the center of the curve. The mean of a skewed distribution or a skewed curve is pulled away from the median in the direction of the long tail. And again, this is something that we saw in the last chapter. So you can see here, if we're looking at our two distributions, in our symmetric distribution, the mean and the median are equivalent. In our skewed distribution, you can see that the mean is pulled in the direction of that tail. A density curve is an ideal description of a distribution of data. It just makes it easier to work with a curve than it does to work with the actual data. So it's like the ideal representation of what we're dealing with. We distinguish between the mean and the standard deviation of the density curves and the mean and the standard deviation computed from the actual observations. So just some notation that we have to deal with. The usual notation for the mean of a density curve is mu, the Greek letter mu, which kind of looks like a fancy M or U kind of mixed together. And we write the standard deviation of a density curve as lowercase sigma, which kind of looks like an O with a tail on top. That's different from x bar and Sx, which represent the mean and the standard deviation of our sample data. One of the most important types of distributions and density curves that we talk about is the normal distribution and the normal density curve. So all normal curves have the same shape. They're symmetric, single peaked, and bell-shaped. Any specific normal curve is completely described by giving its mean and its standard deviation. And as you can see down below in our two pictures, these are both examples of normal distributions, okay? However, they're different in terms of their standard deviations. But they are both normal distributions. They're both symmetric, single-peaked, and bell-shaped. You're going to see the notation for a normal distribution. I'm going to jump down to this last bullet here as capital N and then mu comma sigma. So when you see that, that means that the distribution that we're talking about is normally distributed with a mean at whatever value this is and a standard deviation at whatever that value is. So when you see that notation there, that's just representing that it has a mean at that value and a standard deviation at the second value there. The mean of a normal distribution is the center of the symmetric normal curve. And we call the standard deviation is the distance from the center to the change of curvature points. On either side. The reason we call this a normal distribution is because there's so many things in life that follow this distribution. Whether you're talking about things that are related to probability or things such as IQ scores, SAT scores, even height you could argue is approximately normally distributed. So normal distributions are good descriptions for some distributions of real data. And like I said, they also represent many different types of chance outcomes or things that are related to probability. That's an important concept and something that you'll see a lot during class. There's an in-class activity here that actually you can work through at home if you go to the app that, or the website that's shown there. So if you want to play around with that, we'll kind of review what's said in here during class, but feel free to look at that app to kind of go through what the normal distribution looks like. One of the most important things when we're dealing with the normal distribution is understanding what's called the empirical rule and the percentages that go along with how many values are within 1, 2, and 3 standard deviations of the mean. So for any normal distribution, the area under the normal curve within 1, 2, and 3 standard deviations of the mean, and this is that volcano that you can see at the back of class, is 68% within 1 standard deviation of the mean, 95% within 2, and 99.7% within 3 standard deviations of the mean. Just following through with that, we would expect that 68% would be within 1 standard deviation of the mean, 95% within 2, and 99.7% within 3. That rule is called the empirical rule. And just writing it one other way, approximately 68% of the observations will fall within 1 standard deviation of mu, 2 standard deviations of mu for 95%, and 3 for 99.7. We can see it drawn in here in terms of the actual normal curve. Okay, if this is where our mean is, mu, and we're going down by a standard deviation up each time or up by a standard deviation each time. I want to add some values in here. So we know 68% is within 1 standard deviation of the mean. So that would make 34% here, 34% here, 13.5%, 13.5%, 2.35, 2.35, and then these little values here is 0.15% and 0.15%. So it's important that you know the distributions that are related to that. So let's draw in a normal curve for the fuel fuel efficiency of cars currently registered in Illinois. The distribution, here's our notation, is normally distributed with a mean at 24 and a standard deviation of 6. So when we're drawing in our normal curve here, we'll draw in a number line. There's my normal curve. I'm not the greatest normal curve drawer. And we start by drawing in the mean, which would be at 24. And then we just count down by the standard deviation and up by the standard deviation, whatever that value is. In this case, it's going up by 6 each time, or down by 6 each time. Let's fill in the percentages to make our lives easier when we have to answer the questions that follow. So, we're going to have 34% here, 34%, 13.5, 13.5, 2.35, 2.35, and then 0.15 and 0.15. This is something that you should memorize, whether you memorize it as 68, 95, 99.7, or the values that follow here. You have to know that the normal curve percentages and the empirical rule and all of that follows. So let's answer the questions here in part A. Actually, we're going to go through this in class, but at least you have the curve that's drawn there now. Last thing that we have to discuss is everything that we've talked about so far has been when values fall at exactly those kind of points that are 1 standard deviation, 2 standard deviation, 3 standard deviations above or below the mean. But that doesn't always occur. So we've got some other things that we can use when we're dealing with that. We have what's called the standard normal distribution. So in the standard normal distribution, all normal distributions are the same. If we measure in units of size mu from the mean, or size sigma rather, from the mean mu as the center. So what you see down below here is what we refer to as the standard normal distribution. The standard normal distribution is the normal distribution with a mean of 0 and a standard distribution or standard deviation of 1. If a variable x has any normal distribution with a mean of mu and a standard deviation of sigma, then the standardized value has a standard normal distribution that is normally distributed with a mean of 0 and a standard deviation of 1. We kind of can think of this as our standard distribution of z-scores. So when we're talking about this, we can compare any normal distribution through z-scores and the standard normal curve. So the standard normal curve, like we talked about, is a normal distribution that has a mean of 0 and a standard deviation of 1. And remember, z is equal to x minus x bar divided by sx. This standard normal curve, really, really important when we're dealing with everything that's related to normal distributions. With the standard normal curve comes the standard normal table. So the standard normal table is a table of areas underneath the standard normal curve. It's actually you use calculus to get those values, but they've already done that for us. So now we're not finding values that are exactly 1, 2, or 3 standard deviations above or below the mean, in which case we can just use our empirical rule. Now we're saying, okay, what if somebody is 0.81 standard deviations above the mean? And we want to find the proportion of observations from the standard normal distribution that are less than 0.81. In that case, what we do is we use the standard normal table, or table A. This is in your formula sheet. So what we're finding here is we're finding the probability that z is less than 0.81. When we want to find that probability that z is less than 0.81, we go to our standard normal table. So table A in here. When you're looking at table A, you'll notice on the margins, it has your z, both at the left-hand side and at the top. There's two parts to the standard normal table, okay? You've got this page in here. These are all of your positive z-scores. But remember, z-scores can also be negative because they can go below the mean. So then you have a page with your negative z-scores in here. When you're using the standard normal table, you're going to find the z-score that you're looking for. So 0.81, we would go to 0.8, and then this is your hundredths digits. So for 0.81, let me just start this. So for 0.81, we would go to 0.8, and then down to 0.81, and that would be the value there, or the proportion of observations that are below a z-score of 0.81. And that should make sense to you because 0.81 is above the mean, so we know it should be more than 50%. And this table A always gives the area below that value. So if you look at the shading, that'll kind of give you the clue here. This is giving us the area below the z-score that's being asked. So a z-score of 0.81 has an area of 0.7910 below it. It's always important when you're dealing with this stuff to draw in a picture and shade so you kind of have a visual representation to what you're talking about. So table A will always give the area below or less than that value. So we can answer a question about the areas in any normal distribution by standardizing, aka finding the z-score, and then using table A to go through that. So step one when we're doing this is you want to state the distribution and the values of interest, draw in a normal curve, and shade that area that you're talking about, okay? Make sure that you identify the mean, the standard deviation, and the boundary values clearly identified. Then perform your calculations. Make sure that you always show your work. So you're going to start by finding your z-score. Once you've found your z-score, use table A to find the desired area underneath the standard normal curve and answer the question. We'll do most of the examples in class, but I want to take a look at one more of these. So we're going to do question B here. B says, find the proportion of observations from the standard normal distribution that are greater than negative 1.12. So what we're trying to find here is the probability that z is greater than negative 1.12. So like I said, I'll always draw in a quick sketch so I know what I'm talking about. Here's 0, my mean. Here would be negative 1. So basically what I'm looking for is greater than negative 1.12. So I'm looking for that area there, which means I should be getting something that's significantly higher than 50%. Now I have that. I'm going to go in my chart, my table A, and I'm going to look up a z-score of negative 1.12. So here are my positive z-scores, which means I have to go to my negative z-scores, which are over on the next page. And the beginning of my value is negative 1.1. So I'm looking in this row right here. And I have to go over to a value of 0.02. So I'm looking at a value here of 0.1314. Now keep in mind, that always represents the area below or to the left. Here I want the area above or to the right. So this is not just going to be my answer here of 0.1314. I have to subtract 1 from that. Because what I found here is I found this percentage here, the area below, to be 0.1314, but I want this area here. So to get my answer, I'm going to do 1 minus the probability that z is less than negative 1.12, or 1 minus 0.1314, which is going to get me an answer of 0.8686 as that shaded red region. All right, there's going to be lots of examples that we're going to go through in class related to the normal distribution and z-scores, but now you've got a pretty good foundation of how we deal with the standard normal table and finding percentages that are related to the normal distribution. I'll see you in class for more examples.